Hey everybody, Newland here. Let's talk about the math practice problems we did in class. So, an orbiting object is 385,000 kilometers from a planet. This is the distance of the moon, by the way. That same object is only 3,400 kilometers in diameter. Notice the units are the same. That's important. What is this object's angular size if 1 radian is about 57 degrees? So, right. The equation here is theta is the diameter of the object divided by the distance of the object. So diameter is on top, distance is on bottom. They both have to have the same units. You can see I canceled out the units here. So I put 3,400 for the diameter in the numerator, 385,000 for the distance in the denominator, and we switch to Desmos here, and we'll do 3,400 divided by 385,000, but that's in radians. And in order to get an answer in degrees, which all the answers were in degrees, I need to multiply by 57 degrees per radian. And when you do that, you get, that's kind of small, it's a little better, you get 0.5. So it's about half a degree. So if we go back, about half a degree. So that's how you calculate that. The Earth and the Moon are actually both the same angular size, even though, sorry, not the Earth and the Moon, the Sun and the Moon are the same angular size from the Earth. So there's that one done. Number two, while watching a star, you see that it moves 15 degrees across the sky. So how long have you been watching it? So how do we do that one? We know that there are, so the question was, how long have you been watching it? So we need to know the ratio of hours to degrees. Or more accurately, let's do 360 degrees, which is how long it takes a star to go from, imagine a star is passing directly overhead at midnight. I have to wait 24 hours for that star to be back in that same spot. So, and this is an estimate, by the way, but that'll work. So 360 degrees for a star to go all the way around the Earth, even though the Earth is the one that's spinning. So it seems to take one full day for the star to be directly overhead at midnight once. Tomorrow at midnight it'll be overhead again. That takes 24 hours. If you divide 360 degrees by 24 hours, you get 15 degrees per hour. Meaning, when we go back and look at this problem, that means if it moved 15 degrees, we must have been watching it for one full hour. So the trick will always be either I'll ask you about this much time, how many degrees, or this many degrees and how much time. So that's number two, done. Number three, which I definitely did in a messed up way, but we're going to try it anyway. Here's Eratosthenes. He noticed that the angular measure in Alexandria was 7 degrees, and it's 0 in Syene, so it's a 7-degree difference. We know that the distance between the two places is 800 kilometers. So how do we figure that out? Well, this one's definitely a little trickier, or at least in my opinion. So the way I've been drawing this is here's Alexandria, and imagine we travel around the globe to over here to Syene. We know that what we're talking about is Alexandria is 7 360ths, whereas Syene is 0 360ths. And if you do 7 divided by 360, we get 0.19. 0.19. So that number, that proportion is how much of a circle we've actually if you walk between Alexandria and Syene, which is 800 kilometers, you will have gone that proportion of a circle. If you multiply it by 100, by the way, you'll notice that it's 1.9%, right? Or another way to say that, so this is 0.0194, and I think it was repeating, right? I know I just asked y'all the question and no one's here. Yeah, 0.194 repeating. Or you can think of this as if we multiply by 100, 1.94 repeating divided by 100, right? Well, the deal is that ratio is going to be the same for 800 kilometers divided by the circumference of the Earth, which is also measured in kilometers. So we're setting up a ratio. We know that the proportion of the circle that Alexandria to Syene represents, like if you go that 800 kilometers, you know that's 1.94%. Well, on the bottom, we know that that would be 100% of a circle, which is the full circumference. So I've set up a ratio here, right? So we could say 800 times 100 divided by 1.944 repeating. That would be the circumference of the Earth, right? You could also think of this as cross multiplying. So we're multiplying both sides, or 1.94 times c and 800 times 100, and then you divide both sides by 1.94. So let's throw that into Desmos and see what we get. 800 times 100 divided by 1.9444, repeating 444. There. So that's 41,142. So if we go look at the answer choices, 41,100 is the closest. I recognize that 40,075 is up there too, but that's what Google tells you. So don't select that one. It's going to be the correct answer is 41,100. All right, one more. The parallax problem. So the parallax equation, this is similar to, but not the same as angular size. So let's not mess it up. The parallax, distance equals 1 over parallax. And the parallax to this star that I mentioned was 0.75 arc seconds, which we typically write AS. You can write it as 0.75 arc seconds. You can do that. It's just too much writing. So the distance is going to be, and if you think about this, we could either cross multiply again, we could think of this as d over 1, or you can invert both sides. So 1 over the distance equals the parallax. So if you're having to solve for parallax, you just have to flip the ratio around, right? Now here, we're asking for the distance, so we don't have to do that. The problem, though, is the units are going to be wrong. So distance is going to be 1 over 0.75, but that's going to be in parsecs. And did I say in the problem? Yes, I did. At the very end here, I say there are 3.26 light years in 1 parsec. So in order to convert this, in order to convert this from parsecs, so 1 over 75, well, let's go ahead and do that first. Let's actually get that number. 1 over 0.75, not over 75. So that's 1.33 parsecs. So dang it, y'all. Sorry. That's 1.33 PC for parsecs. The trouble is, though, we need to multiply that by the number of light years, 3.26 light years in 1 parsec, and then the parsecs cancel and we're left with light years. So 1.33 times 3.26, 1.33 times 3.26 turns out to be 4.35 light years. So the distance of this particular star is 4.35 light years. By the way, this is the nearest star to the sun, which is Alpha Centauri. So if we go back and look at our answers, 4 was 1.33 light years when we use that equation. 3 was 41,100 kilometers. 2 was 1 hour because it moved 15 degrees. And number 1, the angular size of the moon in the sky is 0.5 degrees or half a degree. All right, I hope that helps. Reach out if you have more questions.